Okay, so we'll look into layout techniques today. So in order to do the layout for any analog, I mean obviously the PMIC falls into analog category. So you should know what are the different analog layout techniques which are used, because you have to design op amp, you have to design power feds and all those, band gap reference. So what is layout?
Layout is it shows us how to place the components in the chip. How, for example, in the form of layers,
How to place?
Layout is a placement of the components in a chip to get the.
No. So if he is doing layout, his placement is different, your placement is different, then that means only one is correct, other is wrong. Huh?
The way to arrange to get rid of parasitics.
No. Anybody else? What is layout? Huh? Can you send your schematic to Fab? Huh? Fab doesn't understand schematic. Layout tells you how the mask will be created actually, layer by layer. That's it. Placement, routing, all those, your Fab will not understand. Whether you place at other corner, this corner, it doesn't matter for the Fab. It's only the information of the layer mask actually that will be created. That's it. Okay. So any device, you know, if you go to the how the device gets fabricated. So what you have a substrate, on that you grow different layers. Okay. You grow your diffusion for well, then you grow your source and drain, poly, gate oxide, everything, grow layer by layer, and when you complete everything, it will give you this structure. Okay, this is the cross section. So this is your substrate, then you have a P well, N plus, so this is your N channel MOSFET, then this is your gate. Okay, so the poly, between poly and your basically well or substrate, you have thin oxide. Okay, because gate is insulated, so that is basically nothing but gate insulation. Then you have PMOS device here. Okay, so you grow P plus, 2 P plus, so one becomes source, other becomes drain, then again gate, and everything it has to be connected to metal with a contact. So this diffusion basically you connect with the metal and then contacts. Its contacts are nothing but again the metal actually. So when you, since you have a you are connecting one layer with the other layer. So you can think about like you are connecting diffusion with the metal. So you need to create some contact. Okay. Similarly, when you are connecting one metal to other metal, you are stacking up. In between you have oxide. So you have drill into that, just like in the PCB you do. Okay, multi-layer PCB. So that is called via. Okay. So the contact is when you are connecting from metal to any other layer, let's say metal to poly or metal to diffusion, that is contact. When you connecting metal to metal, that is via. And via is nothing but actually hole, that's it. So this is your actual structure. So this is your inverter which has both PMOS and MOS. This is your layout actually. So this layout is telling nothing but what all layers needs to be in your chip and how these layers will look like what should be the spacing between these, what should be the channel length, what should be the width of your transistor, what should be the basically how many contacts you need, what should be the metal width, all those things is defined into your layout. So what you are drawing here, it only makes significance for the Fab, because Fab only can understand these layers, that's it. And you see these multiple layers are there. So when all these masks are created, all diffusions are made metal, then ultimately you get your chip. Okay. So the layout design is the representation of electrical design in form of many distinct geometrical rectangles at various level. The layout is to create the mask that enables the fabrication of chip, that's it. So you are telling your Fab that this is how we create the mask, that's it, and they will create different masks, and based on that they will fabricate the chip. They will not understand, they don't care what circuit you have implemented. So they don't understand whether you have op amp or yeah, they only understand the layers, that's it. And that's what you tell them, this is a layer by layer information I am giving you, now you have, that's how you have to fabricate, that's it. So different rules you need to follow when you are doing especially the analog layout. So one is common centroid. So think about your you are doing an op amp, and in the diff pair you need to match the input transistors. If there is a mismatch, that will create offset. Okay, so they have to be perfectly matched. So now let's say I use a single device M1 and M2 instead of having other two. So you place one in the left hand side, other on the right hand side. So they will see a different condition because the temperature here might be different than this, or when these oxides and other diffusions are grown, they have some gradient actually. So the thickness of oxide here looking at M1 might be different looking at M2. And if you consider a linear variation, okay, so let's say going from left to right, it's going downwards. So the thickness here might be more compared to this, and your VT will change. Okay, and your not only VT, but your, if you are looking at a high frequency performance, your capacitor gate cap will also change. Okay, so in order to match that, what we do, we split them and spread in such a way that those variations are cancelled out. So now let's say this has a variation in the y direction plus, so this is your center where you can say that this is a 0 0. When you go upward, you have delta y variation. When you go left or right, you have plus minus delta x. Okay, so here since it's looking at the top left, so what is your delta y on a y direction and minus delta x in the x direction. So that is the variation. This is this guy is seeing. This will see plus delta y plus delta x. Now I have placed M1 diagonally this. So this will see minus delta y plus delta x. Now if you add them together, they will on an average get cancels out, and total variation in both the devices will be 0. So M1 will exactly look like same as M2 with respect to temperature and process. Okay, so this is called common centroid. You can match as many devices as you want. If you have 3 devices or 4 devices, you can match them. So this for 3 devices. One thing you have to make sure, when you draw the diagonal from one device to other device, all the diagonals should cross at the center. Otherwise, it's not a common centroid. That's why we call it common centroid, because center is common for all the diagonals. So if it's a M3, so the only way to place M3 is at the center. So when you draw a straight line from one M3 to other M3, it will cross at the center. Then if you have unequal number, when I say unequal number, if you have a, let's say M1 to M1 to M2 and your M3 is a single, so then M3 should be placed at the center. Okay, then all these devices will be around this. So it's not necessary that a diagonal, you can, even if you draw a straight line, that should also cross at the center. So another option would be this. If you draw a diagonal from M2 to M2, M1 to M2, M1 to M1, then again it will cross at the center. Okay, and if you have any holes here, then we try to basically make it uniform and put dummy devices. Dummy devices means exactly the copy of the same device, but it's not connected to any signal. Okay, that's why we call them dummy. Okay, so another technique is called interdigitized. Interdigitized means, like, let's say if you have too many units and you want to match them. So let's say too many pieces of M1 and too many pieces of M2. So one way is obviously the common centroid. Other way, you can place alternate M1, M2, M1, M2, M1, M2. Now on an average, the variation from M1 to M2 won't be that much, and so, and since they are placed side by side, and this is only when they are closely placed actually. Okay, so mostly this is used in the resistors, not in the transistor. In the transistor we mostly use common centroid, but in resistors we if you have a, let's say, too many resistors, then it may be a problem put in common centroid, then you can use interdigitized. So on an average they will get cancelled out. Okay, you can combine the two, make it common centroid and interdigitized. So that's also possible. Then dummy cells. So for matching the even let's say here we had holes here, empty spaces, and we put the dummy, but here we don't have any empty spaces, but still you want to put the dummy devices. The reason is, so each device should see the same structure on both sides, even in top, bottom, left, right, all the four sides. Okay, otherwise they won't be matched, and the main reason is actually this may occur due to etching and CMP and doping. CMP is called actually chemical mechanical polishing. When the metallization is done, it's like a polished, and you level everything, so all the rough surfaces are cleaned up. So during etching, what happens, it may undercut, and if let's say this device is not, another device is placed far away from here, and if you place the closer, then this etching may cause more undercut compared to if you have a closer. So if I don't have any dummy here, the undercut here might be different compared to M2, and so it won't be matched there, it will create a mismatch. So that's why you want to create the same condition for all the devices to make sure during fabrication they are perfectly matched. So that's why we cover them, all the four sides, with the dummy devices if it's not seeing. So the top side of this, so that's why we connect it only at the these dummy devices are placed at the border. Okay, because this M1 is seeing M2 on both sides, on four sides it's seeing M2, but this guy is seeing only two sides. So you have to put a one dummy here also on the top and left. Okay, orientation, this is again important thing. So this causes a current mismatch. So if let's say this device is placed vertically and this is horizontally 90-degree out of phase, rotated, so this is not the correct way of matching, because they won't be matched perfectly. So you have to make sure your orientation is same, and then direction of the current should also be same. So if I am placing like source in the left hand side, another matched device I am placing drain on the other side, flipped, then it won't be matched perfectly. So I have to make sure that direction of current should also be same. Okay, so source drain and source drain. So if the source is on the left, the source of the other device should also be on the left. Then dummy routes. So let's say you're routing a signal, and this guy is you're routing from the top. Okay, but it's not necessary that you have a routing signal on the other device also. Okay, so if it's not seeing the other device is not seeing the routing metal, then you have to put the dummy metal, so that both of them see the same metal. So it's all about actually creating a copy of one device, that's it. So if this is seeing something extra, you have to put that on the other device also, and don't connect to anywhere, floating or ground actually, because we cannot connect that to the same signal. So, and the most of the time if it's a high speed lines, obviously these dummies should not be connected to the signal. The reason is they will load that signal. But in order to create the same condition, make sure you have the dummy routes so that they look same, exactly same. So physical appearance should be same for all the devices, all the mesh devices. Cascode. So if you have a cascode, we know that one device is on top of other. So there could be two ways of doing that. One, you can just route M1, M3 separately in the common centroid, and M2 and M4 separately in the common centroid, and connect them together. But the better way is that you route M1 and M2, make a single device, and you can share the source and drain of this. Correct. So this source, the drain of M1 is connected to source of M2. So you can combine them. So you will save area, and matching will also be good actually, because now source and drain are shared here. So you make a single unit of M1, M2 and M3, M4, and then place them in common centroid. So you treat the combination of M1 and M2 as a single unit. So these are some guidelines. So always try to use multiple number of devices with same unit size, and change multiplier as per the requirement. So don't just use a single unit, because otherwise matching won't be. So, and we always use interdigitized or common centroid for better matching. Even number of multipliers help in better matching. If you have an odd number, then you will be left with one device, then the only option is put at the center. But if other also you choose a odd number, then you can only keep one at the center, so other will not match. So that's why I always choose better to choose even number, unless you have only one device. Actually, if you have one device, then you don't have any choice, but if you have more than one, then it's better to choose even number. Dummy cells should be placed around the boundary. Okay. Use antenna diodes. I'll talk about this, what exactly the antenna device is. So this is usually to reduce the mismatch in VT due to charge injection on the gate. So don't route voltages a long way, because IR drop will cause. So always try to minimize IR drop for high current routings. Match signal should be routed together in the same metal layer. Okay, so if you want to match those, let's say you have a fully differential signal, so always try to place them in the same layer and side by side. Match device should be placed in close proximity. Okay, so don't try to create too much space between the two match devices. Make sure they are as close as possible. So there are some rules, like what should be the spacing between one layer to other layer. So follow the minimum rule, don't try to just keep them away. Don't use cells with very small W by L, as they may cause bigger mismatch. So it's obvious, because usually from the process you have some delta mismatch, that is absolute mismatch. So if you have a bigger device, then percentage mismatch will be less. Okay, so if you keep a very small device, then the variation will be large. So that's why whenever you have a match devices, we never try to use a small W by L, but large W by L. Routing should be avoided over the gate of critically matched transistors. The reason is that you don't want to stress the gate, so that's why always try to avoid, especially if it's carrying the AC signal. It may not be a problem with the DC, but with the AC it may load your signals and everything, so that's why. Fingering of transistors. So example is your power FET. You know, how long power FET, the bits look like a order of millimeter. So you cannot keep one. So what we do, we split them in finger. Okay, and the advantage is now you connect all the source with the metal and all the drain. So one side will be source, other side, this top side is a drain and bottom side is a source here. Another advantage is now each fingers will have a shared drain and source. So the moment you split, the overall area will reduce. So you get an area saving also with this, and you can easily connect to the pad or wherever you want to, because now you can draw a wide metal here which can carry larger current, and here if you are putting a wide metal you can put, but then it will be difficult to route actually, because your width is, you think about, like you cannot route a 1 millimeter wide metal, that metal will take all the area, then you won't be able to do anything in that case. But here you can basically stack all the metals on the top and route and connect to the pad. So that's how we do.